Thank you, Cynthia, for inviting me, and welcome everyone. I want to tell everyone over the next 2 evenings, we're going to cover Electron, the basics. We're going to cover a couple lectures that are listed on X-ray imaging, and we're going to do one on mammography. And the times listed there are not quite right. So the basics is going to take us about an hour, 10 minutes. The X-ray imaging will take us about an hour, 10, and mammography about 40. But same 3 hours, just a little bit different distribution. And we're going to stop for the break here in a little bit. But let's start off with a little bit of the basics. So one thing I talk about sometimes is just some of the basic units that you should be familiar with. I've kind of skipped a little bit of that because you can look over some of those, you have the slides, but I just want to remind you of the fundamental forces, right? Gravity is certainly important to us in radiology. I mean, we all know that this must be a left lateral decubitus film because the barium is layering there, and this examination here must have been obtained prone rather than supine because the barium's laying anteriorly in the transverse colon rather than posterior at the hepatic and sigmoid flexures. In addition, another force that's going to be very important to us are the electromagnetic forces, right? We're going to talk a lot about what happens when we apply a voltage across an X-ray tube, both in terms of between the cathode and the anode and across this little filament where we're going to boil off some electrons, and those electrons are going to be accelerated across this very large voltage difference and strike that anode material, and produce the X-rays that we're going to use to image. You know, there are two other fundamental forces. One is the strong force, and that's really what binds the protons and neutrons together in the nucleus. And you know it must exist, right? Because two positively charged things should repel each other because of the electromagnetic force. But yet they're bound together tightly in that nucleus. And so for us, I really just want you to realize that that must exist. It must be stronger than the electromagnetic force in order to do that. The weak force is something more subtle, and we actually need it to describe radioactive decay, but really its purpose is kind of beyond the level of the lectures that we're going to be talking about. But here they are in their relative magnitude, okay? The strong force, stronger than the electromagnetic force. Both of these are stronger than the weak force. And gravity, the weakest of all We're going to talk a lot about energy. We're going to talk about energy of X-rays that we create. And normally, outside of X-ray imaging, if I mentioned energy to you, you'd probably think of kinetic energy, right? The energy of motion. You know, how much energy does a car have? And that's really determined by the mass times the velocity that it has squared, the 1/2 term there. And those units are usually given in joules, right? A joule is a kilogram meter square per second square, and that's much too large a unit to be useful to us in radiology. We're going to work with something called the electron volt, and it's the kinetic energy that an electron has mass, remember, when we accelerate it across a voltage difference of 1 volt. So here we have an electron, we accelerate it across that voltage difference of 1 volt. When it strikes that positive terminal, that cathode there, that electron had a kinetic energy of 1 electron volt, okay? If we accelerated it across 1,000 volts, it would end up with a kinetic energy of 1,000 electron volts. Also, you know, energy can exist without mass, right? That kinetic energy equation implied to you that, well, you've got to have mass to have kinetic energy, and that's true, but energy can exist without mass, and we're going to see that a lot with electromagnetic radiation, such as radio waves that you've already probably talked about when Dr. Serlin talked about MR imaging. Certainly visible light, part of the electromagnetic spectrum, very important to us. And then the X-rays and gamma rays that we use to do our imaging. There's also another important energy to us as we talk about X-ray imaging and especially nuclear medicine, and that's the rest mass energy of a particle. So if I could take all of the mass of an electron and convert it completely into energy, okay, that would give me 511,000 electron volts of energy. You can calculate that by knowing the mass of the electron and just applying the simple equation E equals mc squared, okay? So it's mass times the speed of light squared. And that number should be very recognizable to you, because when we have a positron, which has the same mass as an electron but the opposite charge, right? It's the antimatter equivalent of an electron, and it annihilates with an electron, we give rise to two 511 keV photons that we're going to use to image in PET imaging, okay? We're going to talk a lot about electricity. In electricity, right, voltage equals current times resistance. So here's a voltage. Think of it as a battery. You apply it across a resistance. Perhaps that's a light bulb. Perhaps that's the filament in an X-ray tube. Perhaps that's the resistance between the anode and cathode in an X-ray tube. But once you apply that voltage, the current that flows is determined by whatever that voltage was and whatever that resistance is. So in mentioning two of those, right, I have determined what the third one of those is. And I'll make a point of that as we look at some X-ray tubes and talk about some of the fundamental little circuits that are there. So here's one. And really there are three electrical circuits that are going to be involved here. One is we're going to apply a little voltage, a small voltage, across this filament like in a toaster or like in a light bulb. And when we do that, it's going to heat that filament up, and electrons are going to get boiled off the surface of that. And with nothing else present, they really wouldn't do a whole lot. So we also apply a large voltage between this point on the filament, negative terminal, or the ground here, and the positive terminal on this anode. And that's on the order of, right, 100,000 volts, right? And that electron is now accelerated towards that cathode and strikes it with a lot of energy. How much? Well, 100,000 electron volts, 100 keV when it strikes that. That's how much kinetic energy it has. That creates a lot of heat that ends up dissipated in this anode here. And so we really need to help dissipate that heat, and one thing we do is then rotate the anode. So there's another circuit, right? There's a voltage that we apply across a motor here that rotates that anode so that the heat doesn't all get deposited at a single spot. But all three of those are just examples of little electronic circuits. In terms of electricity, I also want to mention the concept of power. And power, if we know what the voltage is across an electric circuit and we know what the current is, if we'll just multiply those two times each other, we'll get an idea of the power. The only thing I really want you to realize about this is a lot of our X-ray equipment consumes a tremendous amount of power. Typical voltage across an X-ray tube, 100 kV. Typical amperage, 1,000 milliamps or 1 amp, that's 100 kilowatts of power, right? Think about a 60-watt light bulb in your house, right? This is a tremendous amount of energy it takes to run an X-ray tube. So just in general, in terms of this first little introductory part, I want you to know your units and their appropriate values for different applications. For example, range of voltages on an X-ray tube, right down in the 30 kV range for mammography, up to the 120, 140 kV range for CT, maybe 80, 100 for some X-ray imaging. I want you to understand the range of MAs for a CT study, the energy of photons of technetium-99m. If I say that to you, you all ought to be able to just tell me 141 keV. Effective radiation doses for some different studies, speed of sound in tissues, and realize that some of these are easily confused, right? keV, which is a measure of energy, right, as a unit of energy, is often confused with kV or kVp, which is a measure of voltage. The concept of MA, which is a current, and milliamp seconds, MAS, which is a charge, right, when we multiply by seconds, are often confused. And then some of the units of dose are also confused with each other. We'll talk about those when we talk a little bit about radiation biology. The next thing I want to talk about is the atom. And just in terms of basics, right, we're going to, so long as we understand the Bohr model of the atom, we don't need to get much more sophisticated than that to understand the physics we need to know. So for us, it's really going to be almost like planets orbiting a sun, right? We've got the nucleus, the sun, that consists of protons and neutrons, and we can view these electrons as orbiting around that, if you will. it's a good idea for us to keep in mind some of the properties of those different elements that are going to come into play, those that comprise the atom. The electron we already talked about has a negative charge, and it has a mass that's quite low, a relative mass of 1 here. I'm going to look at the mass of the other fundamental particles there relative to that. So a proton has the same magnitude of charge, but it's positive, it's opposite in sign. And notice its mass, it's about 2,000 times more massive than an electron. And so its rest mass energy is quite a bit larger, right? We already talked about the fact for an electron that's 511,000 electron volts. And notice here, this is in the mega electron volt range as opposed to the kilo electron volt range. Neutron, very similar mass to that proton, almost identical. But remember, has no charge. So all atoms can be described using this notation. We're all familiar with it, right? X is a unique letter, O for oxygen, C for carbon, or sometimes a couple of letters for some of the elements. A is the atomic mass number, the number of protons plus the number of neutrons. It also happens to be the number of grams per mole that atom would weigh. Z is the atomic number. It's the number of protons, and of course in a neutral atom it's also the number of electrons. And this notation is a little bit redundant because O, by definition, is the atom that has 8 protons, right? So we don't really need to put an 8 subscript down here, and so oftentimes oxygen is just listed as O16, if you will, without that subscript, just the superscript there. And remember from back in your chemistry days how these orbital electrons line up. Remember, we've got this inner shell that contains 2 electrons we call the K shell, and then just outside of that we've got our L shell that contains 8. So this is our second shell, the L shell. So if we put a 2 in here for n, 2 squared is 4, times 2 is 8. So now if we go to the next shell, 3 squared is 9, times 2 is 18, and that's how many electrons the M shell contains. It's the electron shell structure of atoms that determines their chemical behavior. And that's how Mendeleev constructed the periodic table, right? These are all things that have full outer shells, and they tend not to be very chemically reactive, right? These are things that have an extra electron, just 1 electron in the outer shell, and they'd really love to give it away. And in fact, they'd love to give it to these guys right here who are missing an electron from that shell. So that's a chemical behavior. It's not extremely important to what we're going to be discussing, but I just wanted to mention it. Something that's more important to us is the notion of electron binding energy. How tightly are these electrons held in place in the atom? Well, think about it. A lot of that has to do with the electromagnetic forces that we talked about, some of the Coulombic forces. So the closer the electron is to the nucleus, the more tightly bound it's going to be, right? And so the K shell electrons are more tightly bound than the L shell electrons. And then the more positively charged the nucleus is, the more tightly bound those electrons are going to be, right? The more positively charged the nucleus is, those negatively charged electrons are going to be more bound to it. So removing an electron requires an energy that's greater than that binding energy. If you don't have an energy greater than the binding energy, you can't remove the electron from the atom. And I put this list of binding energies here, not because I want you to memorize anything from them, but I want you to look at the number for hydrogen. What if I want to take an electron from hydrogen? Well, that's going to take about 13.5 electron volts of energy. And then when we look at what is the level for ionizing radiation, it's going to be right around in that number, right? That's the smallest number that occurs in this table. So radiation that has energy below around that value in electron volts, radiation that's less energetic than that, isn't going to be able to ionize an atom. Okay? And then the other thing that's important to us are these binding energies on some of these materials. Barium, iodine, that we use for contrast agents. Those K-shell binding energies are very important to us because part of the reason they work well as contrast agents is that these K-shell binding energies determine the photoelectric effect, when the photoelectric effect is likely to occur. And that's really what makes these contrast agents appear much more highly attenuating at those energies. So I wanted to show you that. And then the other thing is we have some really interesting things in nuclear medicine, like we image with thallium, and as thallium decays, it does something really interesting, and I'll remind you of that on Saturday when we talk a little bit about nuclear medicine. So these binding energies become important to us for those reasons. You know, in chemistry, we learned about the importance of removing or adding outer shells electrons from atoms, you know, creating ions, right? In physiology, this can have fairly deleterious effects. You know, if you remove an outer shell electron, you create some of these ions, some of these free radicals. The hydroxyl radical, unfortunately, we're about 70% water, right? So you can create a lot of OH minus ions there, and they can result in significant damage to biologic tissues. So let's look a little bit about what happens if we start removing electrons from atoms. So this is tungsten, right? It's got 74 protons, and it's got, you know, it's 110 neutrons, 184 minus the 74. This is the sum of the protons plus the neutrons. I'm going to start to draw in its electron shell, but I'm going to give up very quickly because I don't want to draw shells of 74 electrons, and we'll make our point with a little subset of those. So it turns out that the K-shell binding energy for tungsten is about 69.5 kiloelectron volts. And the L-shell binding energy is about 12 kiloelectron volts. So now what if we had some electromagnetic wave or some particulate radiation that possessed enough energy to kick one of these inner shell electrons out of its shell? What would happen next? Well, what would happen is that one of these L-shell electrons, or perhaps one of the M-shell electrons, would come in and fill that space. And after that came in to fill, we'd get a release of characteristic electromagnetic radiation. Here in the X-ray range, 57.5 keV. Notice the difference between the two binding shell energies. And this is called characteristic X-ray energy because it is characteristic of this particular atom. If we looked at a different atom, it would have different K and L shell binding energies, and those differences would be unique to that particular atom. So if you looked at some material out in space here on Earth, giving off radiation after you shot radiation at it, you could tell what the material was made of by looking at where the bands of characteristic radiation lie. You know, that's not the only thing that can happen. Sometimes when we kick that out, as we get this transition, rather than getting that 57.5 or so, 57 keV characteristic X-ray energy, that energy gets transferred to one of these outer shell electrons, and it heads off with a kinetic energy that's equal to the difference of these, but also minus its binding shell energy. And these are referred to as Auger electrons or Auger electrons, depending upon, I guess, whether you're from France or the United States, right? And the importance of those is now we've got a very energetic electron traveling around in these tissues. And if this is biologic tissues, it's going to wreak a lot of havoc there. And so I want you to keep that in mind, right? We're talking about what happens not just in tungsten, but this is also the same kind of thing that could happen if this were a biologic tissue. So characteristic radiation, we mentioned this, they have those unique values, and I mentioned that each element could be recognized by those. You know, we can't predict precisely which event will occur, but we do know for a particular atom and imparting a particular energy on it, we do know the probability that each will occur. And heavier elements tend to be more likely to emit characteristic radiation, while light elements are more likely to emit Auger electrons. Again, important to us because as biologic tissue, we're predominantly made out of lighter, right, elements. So what happens When we remove that inner shell electron, we talked about when the difference in binding energy is large, we can get those characteristic X-rays, right? When the difference is quite small, and this isn't necessarily true for atoms, but sometimes in molecules where some of these electrons are shared and the energy that binds them between the different atoms in the molecule, the binding energy is even a little lower. The binding energies might be in the few electron volt range. And that's in the visible spectrum. And these are tissues that either scintillate or phosphoresce, right? If you irradiate them, they now give off electromagnetic radiation in the visible light range. So when we talk about X-rays, realize we're just talking about a phenomenon that's just much higher up in the electromagnetic spectrum in terms of energy than visible light. But here this is also giving off some of the same kind of stuff. I know we wanted to take a little break. Lou, we're going to go a little bit longer here. Is that you set me to? Okay, good. All right, so let's start talking about electromagnetic radiation here. So electromagnetic radiation is energy that travels through space or matter. Radiation is energy that travels through space and matter. There's two types, particulate, so that's stuff that has mass. It may have charge. Remember, the neutron doesn't have any charge, but the positron, the alpha particle, those have charge. The electron, it fits in that class as well. And then the electromagnetic radiation, the pure energy, has no mass or charge. So let's just talk a little bit about electromagnetic radiation specifically now. Remember, no mass, it's unaffected by electrical or magnetic fields, travels at a constant speed in a given medium, and that maximum speed occurs in vacuum and is given, it's about 3 × 10⁸ meters per second. In other media, the speed is a function of the characteristics of that media. And it can propagate through matter, and as a matter of fact, the behavior of electromagnetic radiation with matter is quite complex. You know, down low at the radio wave end, that radiation really tends to pass right through us. When you get up to the microwave end, it can interact with matter. I mean, that's how a microwave oven works, but it really works by rotating part of the atom, and you can vibrate or rotate that behind. So you can get microwave energy to deposit in the tissues as heat, if you will. As you go higher up, things change again. At the X-ray energies, things interact sometimes. Sometimes as it gets more energetic, it's more likely that it may just pass through. The interactions, absorption, scattering, and we already mentioned radio waves, going to be important to us in MR, visible light, X-rays as examples. One of the first things I want to say is, right, notice this travels in straight lines, right? Travels in straight lines. If we're in a vacuum or in air for the most part, it travels in straight lines. And if you think about that, that really explains to you one of the first things you're probably told in radiology, the inverse square law. You know, think of a little point source of radiation, a little bit of technetium sitting in the front of the room, right? And it's emitting 141 keV gamma rays. And for the most part in air, in vacuum to be more precise, those gamma rays travel in a straight line away from that. And so if you take a look at how many are passing through a particular area when you're a distance r from that source, now if you move twice as far away, notice those 9 gamma rays are now spread out over 4 times as much area. Or if you will, if you were the same size, like this letter A in this picture, only 1/4 as many of them would pass through you, right? So as we double our distance from the source of radiation, right, the dose that we're exposed to decreases by the square of that distance, okay? But this is true for all electromagnetic radiation, right? I mean, this is true for radio waves. So if the source of radio waves is sitting at that point, where do you want to put your MR coil? You want to put it as close as possible to the source of those waves, okay? So true for all electromagnetic radiation. Electromagnetic radiation, you know, has both wave and particle-like behavior. And sometimes as I talk, I'm going to talk to you and I'm going to say a gamma ray, and that sort of accentuates the wave-like properties when I say that. And other times I'm going to say to you an X-ray photon, and that sort of accentuates the particulate properties of electromagnetic radiation. Because the truth is, at this subatomic level, you know, there's this duality where things can behave both wave-like and particle-like that's really unfamiliar to us in the macroscopic world, where, you know, you kind of behave like one or the other. Like any wave, the velocity of electromagnetic radiation is equal to its frequency times its wavelength. But for electromagnetic radiation, you know, that velocity is constant. It's the speed of light in a vacuum. And it propagates as a pair of magnetic fields. And that's only important for us. I want you guys to remember that if I have a time-varying electrical current, then I have created a magnetic field, right? Or if I have a time-varying magnetic field, I can create a current. But the first way that I said it is more important to us, because that's how we're going to make our gradient coils and things work in the MR scanner, right? We're going to put a current through some wires, and that's going to change the nature of the magnetic field, the add to or subtract from the main magnetic field of the magnet. The wave-like properties of electromagnetic radiation are probably best understood by this double slit experiment. I mean, think about it. If light were a particle, right? Light is an electromagnetic wave. If you shot particles through this slit, then oftentimes they just hit this wall over here, except occasionally they'd go through one of these other slits and they'd hit this screen. And they'd have to hit this screen in a fairly small region right in here. And the same thing, they could, depending on your angle, sometimes make it through both slits with the bottom slit here, and you'd see the distribution of those particles hitting in this area. But that's not what we see. We see something that looks much more like the behavior of a wave, where that wave of light propagates out, and then when it hits this wall with these two slits, we get two individual wave fronts propagating through each of those slits, and those constructively and destructively interfere with each other to create this pattern on that screen. So just intuitively giving us the idea that light, electromagnetic radiation, has a wave-like property. That particle-like property I want to show here, and as soon as I finish, we'll take a break, Lou, with this next slide. Here's the best example I can give you that, and that's the photoelectric effect, which is going to be really important to us. You know, potassium, the M-shell binding energy of potassium, the lowest energy at which any of its electrons are bound, is 18.3 electron volts. And you can beat potassium all day long with multiple 18.2 EV photons, okay? Multiple ones. They never add up together like waves might and knock out one of these electrons from their shell. But once you go above that threshold, you immediately can kick out some of those electrons from the shells of potassium, emphasizing that particulate nature of electromagnetic radiation. Okay? So that's the photoelectric effect. It'll be really important to us in a little while as we talk about some of the X-ray interactions with matter that happen when we make a radiograph. So I show this image just to kind of remind you where the visible spectrum is. You know, I don't particularly like this image because it lists X-rays and gamma rays as being separate entities, and they really can have very similar entities. And for us, we're really going to designate them based on how we produce them. But also to give you an idea of, you know, MR is really interesting, right? We have electromagnetic phenomena with a wavelength the size of a kind of a skyscraper, if you will, and yet we're imaging, you know, the protons in water in fat predominantly. And then up here where we are, you know, we're on about the level of the diameter of an atom. I like this a little better, right, because it shows the overlap between X-rays and gamma rays. Our visible spectrum right here, the ultraviolet, infrared. So let's talk a little bit about electromagnetic radiation. The gamma rays are really emanated from the nucleus of radioisotopes, and we use them to make images of the distribution of those radiopharmaceuticals within the patient. So anything that's, you know, this electromagnetic phenomenon that's produced from the nucleus, we're going to call a gamma ray. And X-rays are produced outside the nucleus. We're going to talk about how we get those in an X-ray tube, but we use them in radiography and CT. We've already mentioned the radio waves and visible light. I want to mention ionizing radiation. Right? Electromagnetic radiation of a higher frequency than the near ultraviolet has enough energy per photon to remove electrons from atoms and molecules. if you look at that, right, in water, that requires about 12.3 electron volts, right? They're sharing some electrons there. So it's a little bit lower than what we saw in hydrogen. And if you look back at the chart that I had, or on this one right here, where we've got that ionizing radiation, it falls right in that range that where we were talking about, around 12 electron volts or so. So below that level, there's just not enough energy to remove electrons from the shells of atoms or molecules. So let's talk a little bit about how radiation interacts with matter. And I want to start off by saying, look, this is all matter. Some of this is going to be important to us when we talk about how it interacts with biologic tissues. Some of it's going to be important to us when we talk about how radiation interacts with materials like tungsten in an X-ray tube. And some of it's going to be important to us when we talk about how radiation interacts with scintillators in detectors like digital imaging detectors or a PET CT scanner. So radiation interaction with matter. Whoops. So energetic charged particles, right, interact with matter by Coulombic interactions and lose their kinetic energy via excitation, ionization, and radiative losses. So these are things that have mass, particulate radiation, mass and charge here. So here we have an energetic charged particle, and as it passes close to an atom, it may excite one of these outside shell electrons, and that electron may move to a slightly higher shell temporarily and then move back. And it may give off some emission of radiation as it returns to that lower level. And this is usually in the infrared range. So this is heat. This excitation results in heating. And the vast majority of the interaction in human tissues results in this occurring, frankly, in most materials. Ionization, of course, a very similar thing happening, but now the interaction is strong enough so that that electron breaks free, creating an ion. And we've already talked about what happens once this occurs, right? Once this occurs, we can get some of those characteristic X-rays and Auger electrons. And approximately 70% of the interaction of charged particles is deposited via excitation. When ionization occurs, that ejected electron might possess sufficient energy to kick additional electrons out of their shells in the neighborhood, in neighboring atoms. And we refer to those as delta rays. The importance of that to us is, right, if I kick an electron out of its shell and impart to it a lot of kinetic energy, it can end up resulting in some fairly deleterious effects to the surrounding tissues. And I mentioned the fact that with both these processes, we can get those characteristic X-rays and those Auger electrons. When we talk about dose radiobiology, I'm going to talk about linear energy transfer, because really the effect that radiation is going to have on biologic tissue is going to have to do with how much energy it transfers to that tissue per unit distance that it travels. But I just want to mention that things like electrons that have relatively low mass and they're charged, they travel a very awkward path, bouncing around. And I usually say, you know, think of the billiard ball bouncing around, striking other billiard balls. And, you know, here think of a bowling ball hitting other billiard balls, right? It really just keeps going the direction it's going as it strikes everything in its path. And those are things that are quite massive and have a lot of charge. Let's say like an alpha particle, right? The nucleus of helium, 2 protons, 2 neutrons. The proton falls in that group as well, by the way. So what about radiative interactions? Because this is going to be important to us in terms of how we generate X-rays. Well, charged particles can also undergo interaction with the nucleus of that atom, right? And so here we have this charged particle. It's going to swing close by the nucleus of this atom, and its direction is going to be changed by the interaction of its charge with the charge in the nucleus. And that's going to change the kinetic energy of that particle. So it's reduced, let's say, to 40 keV in this example. But conservation of energy says we're going to get the emission of this 100 keV photon. So notice our initial charged particle has slowed down, and we've gotten production of this radiation. And that's the Bremsstrahlung, or braking radiation, that we see produced as we slow down and change the path of that particle. It turns out that when the energy of that electron is low, that Bremsstrahlung radiation is emitted preferentially in a particular angle. Now, this picture is a little bit misleading, and I want to make sure to say, right, when this electron comes in here, I want you to realize that we get radiation, right, if this is an material consisting of many of these atoms, and we're bombarding it with particulate radiation, we're going to get Bremsstrahlung radiation that heads in all different directions. But it doesn't quite head in all different directions equally, okay? It has a slight preference for this direction. And if you'll notice, that's where we put the X-ray window on our tube, right? Why does our tube have the X-ray window in the location it does? It does here because that's the greatest number, where the greatest number of those X-rays are produced. What about other things? Well, the positron undergoes annihilation with the electron. There's another thing that has mass and charge, same mass as an electron, but opposite charge, the antimatter equivalent. That interaction is going to be very important to us in PET imaging. The neutron we haven't talked about. You know, it has no charge, but it has mass, and so it can transfer energy via collisions or be captured by the nuclei. And when it has collisions, frankly, what it does is it ends up launching out some of those other particles, be they electrons, which we've talked about here, or protons or other things. Neutrinos I'm not going to talk about. They have no charge, extremely low mass. They don't really interact with anything. I mention them only because I want people to keep neutrons and neutrinos separate from each other, okay? So what about X-ray and gamma ray interactions, right? We just finished talking about particulate radiation interacting with matter. Now I want to talk about electromagnetic radiation and how it interacts with matter. And those interactions are complex. They depend on the X-ray energy beam, the energy of the X-ray beam, the particular material that we're talking about, its atomic number, and then also its electron density. So how many electrons are located in a cubic centimeter of that tissue? This is an equation for electron density. Remember, this is just density, so that's the amount of grams per cubic centimeter. This is Avogadro's number, so that tells you how many atoms there are, right, per gram. This is the atomic number. That tells you how many grams there are per cubic centimeter. So when you cancel these the things out here, you've got the number of atoms per mole, and so now multiplied by the grams per cubic centimeter. You've canceled out the grams there. So you've got the number of atoms per mole when you make this multiplication. And then if I multiply by Z, well, that's the number of protons, but it's also the number of electrons in the neutral atom. So I have the number of electrons times the number of atoms per cubic centimeter. So this is the density of the electrons. It turns out that the molecular structure of material really is negligible in terms of its effect on the attenuation properties up at diagnostic X-ray imaging, right? Any of you who wear glasses realize it's not negligible down at the visible light range, right? You can bend light, refract light with a pair of glasses there, but the molecular structure is really negligible where we're going to be talking about. In diagnostic imaging, X-ray photons predominantly transfer their energy to electrons of the atoms, right, which are going to lose their energy by interacting with other adjacent atoms. In other words, X-rays, when they interact with matter, are going to produce energetic electrons. And how do energetic electrons interact with matter? Via the ways we just discussed when we talked about particulate radiation. But I want you to keep that in mind, right? Because when we image with X-rays, one of the first things that's going to happen inside the patient is we're going to create a bunch of energetic electrons. That's going to deposit the dose in the patient there. When we take an image, about a third of the X-ray energy is going to end up getting deposited in the patient as dose. I'm sorry, about 2/3 of the energy. About 1/3 of it's going to be scattered back out of the patient, and only a small fraction of it is what we're going to use to actually make the image of the patient. In air, an electron with kinetic energy 100 keV goes 10, 15 centimeters before it is interacted enough that it stops, if you will. In soft tissue, that distance is only 1/10 of a millimeter about. That's very helpful, right? I think most of you as a resident, right, you've had to do 6 I-131 doses to patient, right? And the thyroid accumulates I-131 very nicely, right? So those electrons, those energetic electrons that are radiated off in the beta minus decay of I-131, they interact and give all their energy off within 1/10 of a millimeter, typically, of where they're produced. So it treats the thyroid very well locally for that reason. All right, so now remember, we're talking about X-ray interactions. I've just made the point that X-rays interact with matter, and the first thing they do is produce energetic electrons. And I don't want you to forget that, because that's where the radiation dose to the patient comes from there. But let's talk about how those X-rays do that. The first thing I want to talk about is coherent scatter. So in coherent scatter, this X-ray interacts with that atom kind of as a whole. It kind of, if you want to almost think of it, you know, it vibrates it to a slightly excited state, and as that atom relaxes back to its normal state, it gives that energy back off, but in a slightly different direction. Okay, so coherent scatter changes the direction of the energy, but not by a whole lot. We're lucky because coherent scatter really is a minority of the interactions that occur at diagnostic energies. Much more at mammography, KEVs, energies, but very little up at the diagnostic energies for, let's say, abdominal plain film, CT, those kind of things. So we're going to ignore it for our purposes. Here it is. Here's the total interaction from some of these different events. Notice that classic scatter, coherent scatter, Rayleigh scatter really drops off pretty quickly, and at 100 keV, it's really dominated by Compton that we're going to talk about. And photoelectric dominates it fairly well lower down there, so we're going to ignore it. Another thing that can happen when you have an energetic X-ray or gamma ray photon is it can end up interacting with the nucleus and producing a pair of an electron, ejecting an electron and a positron from the nucleus of the atom, this pair production. This doesn't happen. It should make sense that in order to have that occur, you've got to have an X-ray or a gamma ray that's at least 2 times 511 keV, which is 1.022 MeV that I have there. And so for us at diagnostic energies, this really is not an issue, right? If you were maybe doing radiation therapy, this would be more of an issue to you. So here's pair production, incident there. We get that negatron and that positron, or that electron and positron produced there. Another thing that can occur is photodisintegration. And now here, the X-ray is so energetic that it actually breaks the nucleus apart. And it takes about 15 mega electron volts to even be able to do this. So this is way above the energies that we're interested in. And it just makes sense. If you look at the binding energy per nucleon in the nucleus of an atom, how much energy does it take to keep the nucleons bound together by the strong force, you can see it's in the range of 789 mega electron volts per nucleon. So you've got to be quite energetic to make that happen. So that leaves us 2 things to talk about: photoelectric interactions and Compton interactions. And before I talk about those 2, those are the 2 that are important to us, I want to say something about the image formation process. Look, in order to make an image, right, in order to make an image, some of my X-rays have to go through the patient, and some of them have to be stopped by the patient, right? If none of them made it through the patient, we would just make an image that looks like a shadow of the patient, right? It would just be a black area, if you will, where none made it through, with white in the rest of the area. If all of them made it through, the image would just be uniformly white, neither of which is helpful. We rely on the fact that there's differential absorption of those X-rays as they go through the patient. Okay? It would be great if when the X-rays interacted with the patient, they were just stopped and didn't continue on. Okay? And there's one effect that actually is going to do that for us, the photoelectric effect. Unfortunately, there's another effect where they impart some energy and then change direction. They scatter from there. And they may scatter and still hit our image plane, and that's going to result in a degradation in the quality of our image, reduce our image contrast. And that's the Compton scatter that does that. We wish we could really minimize that if at all possible. We'd like to be able to understand how can we select our kV, our kilovolt or kilovolt peak on the X-ray tube, our MA, our type of detector, our type of filtration, our type of contrast, all these things to really make those interactions happen the way we would like them to happen to get the best possible image. That's our goal. So let's talk about the photoelectric effect. With the photoelectric effect, when this energetic X-ray photon comes in, it's going to interact with one of these inner shell electrons typically, and it kicks that out of its shell. Whoops. That's the photoelectron, right? So there's our 65.96 keV photoelectron. And what's that going to do? It's going to deposit all its dose there in the patient very locally, like we already talked about. That's how particulate radiation interacts with matter. Okay? That L shell electron's then going to come in and fill that L shell, and we'll get rise to some characteristic radiation. You know, if we're talking about this interaction occurring in high Z materials, that characteristic X-ray energy might be fairly high. But in human beings, where calcium is about the highest Z material you can have, notice that energy is quite low. So most of these, that dose gets deposited in the patient as well. The photoelectric effect, the probability that the photoelectric effect is going to occur is roughly proportional to the Z cubed of the material divided by the energy cubed, okay? Divided by the energy of the X-ray cubed. So as the energy of the X-ray goes up, this drops off very quickly, right? As we go from 10 keV to 100 keV, 10 times 10 times 10 is 1,000, 100 times 100 is 10,000, times another 100 is, 10 million, right? The denominator gets small very quickly. The probability of this interaction drops precipitously. Okay. It turns out, though, what's interesting is there's an abrupt increase in the probability of the photoelectric effect just above the K-shell binding energy. Remember I showed you those binding energies and I told you they'd be important to you, and that's why. The probability that the photoelectric effect is going to occur, it's not a continuous function that just gradually goes down 1 over E cubed. It has some discontinuities in it that correspond to the binding shell energies. And we can take advantage of those by using a particular X-ray energy and using a particular contrast material that have K-shell binding energies matched to the X-ray energies to really take advantage of that, okay? So here are some important K-shell binding energies. You know, very low for human tissues like oxygen. But I put them up here for iodine. Notice about 33 keV. Barium, 37 keV. Lead, 88 keV. Here's a picture. This is cesium iodide. So this is relatively high, right? Iodine we use as a contrast agent. Cesium's fairly close to it on the periodic table. So the K-shell binding energies are fairly high, much higher than for biologic tissue. And notice here the photoelectric effect and the Compton effect, they're about the same contribution to the total attenuation of the X-ray beam, up at around 200 keV. We're going to see at biologic tissue that occurs much lower down than that because biologic tissue has a much lower average Z. So let's talk a little bit about Compton now. So in Compton, the X-rays tend to interact with those outer shell electrons. The X-ray photon gives some of its energy to one of those outer shell electrons, typically breaking it from its shell and giving it some kinetic energy. And that scattered electron loses its energy by interacting with those adjacent atoms through those mechanisms that we talked about: excitation, radiation, interactions. The X-ray photon then has less energy and unfortunately heads off in a new direction, right? So here's this case, right? Now we come in, we interact with this outer shell electron. It heads off with some kinetic energy. Let's say we gave it 5 keV of energy. Well, now if we want to know the energy of the photon after that, this X-ray photon after that, we've got to subtract the binding shell energy plus the kinetic energy that we gave this electron, and if we do that, we get about 94.56 keV that heads off with. And unfortunately, it now may strike our detector, but you know, the focus of our image has to do with we're using this point source of radiation, and so now this scattered X-ray hits our image plane, and it looks like it came from a completely different direction than the original X-ray actually did. So that scatter degrading our image. They maintain a large percentage of their energy, even at large scattering angles. So, you know, it doesn't help us to kind of think about, well, could we get rid of them at the detector if we could somehow do some energy discrimination? We'd have to be really good to make that happen. 100 keV Compton scattered X-ray at 90 degrees. So if we started off at 100 keV, it Compton interacted and scattered off at 90 degrees, it still has 83.6 keV of energy. These will escape the patient, right? And that's bad for us when we're doing fluoroscopy procedures, right? When we're doing IR, because these highly energetic scattered X-rays are going to hit us. They're going to scatter 180 degrees, 90 degrees from the patient and have enough energy to escape their body and potentially interact with us. These account for the majority of scatter at diagnostic X-ray energies. The probability is proportional to the electron density of the atoms, and it drops off as 1 over E, approximately 1 over E, not 1 over E cubed like the photoelectric effect. So as energy increases, photoelectric effect is dropping 1 over E cubed, Compton is dropping 1 over E. So very quickly, Compton dominates the effects. They're both equal to each other. Remember, I showed you cesium iodide. At cesium iodide, they're both equal to each other at about 200 keV, because those materials have much higher Z than human tissues. In human tissues, soft tissues, they're equal to each other at about 25. So here's photoelectric effect, here's Compton, here's where they're equal to each other, the percentages, right, this is a log scale, so this is right down around 25 keV. That's great for us in mammography, right? But that, unfortunately, when we get up to CT energies or so, we really are not able to take as much of the advantage of the photoelectric effect as we'd want to. So I've mentioned attenuation and linear attenuation a couple times, I've said them, and I haven't really told you what we mean, right? The linear attenuation coefficient is the rate at which X-rays are removed from an X-ray beam. A monochromatic, single energy beam, let's think, an ideal case. As I pass it through tissue, if I put 1,000 in, how many do I see on the other side that are completely unaffected? We've mentioned the fact that some Comptons may still get through, but they've been affected. Their energy is less. How many make it through completely unaffected? It turns out that that's just a kind of a decaying exponential, the same kind of thing that we see in radioactive decay. The number of X-rays that make it out is a decaying exponential that has to do with the attenuation, the linear attenuation of the material, and the thickness of the material that you've passed through. How could we figure out what that is for particular materials, for a particular energy of X-rays? Well, here's our monochromatic X-ray source of a particular energy. Just take yourself some layers of that material, let's say 1 centimeter thick, and first put down 1 layer and see how many X-rays you detect, know how many you transmitted. And then put down 2 layers. How many of the transmitted now do you detect? Put down the 3rd layer. And if you drew that for different numbers of layers, centimeters thickness layers, you'd make a curve that looks like that, a decaying exponential like we talked about. And if you just plotted that on a semi-log plot, right, The slope of that line right there is the linear attenuation coefficient that we're talking about, the rate at which we remove those things from the beam. Now, that linear attenuation coefficient really is the sum of the behavior of those 5 different things that we talked about. What's the linear attenuation coefficient due to Rayleigh scatter? What's the linear attenuation due to the photoelectric effect, to Compton, to pair production, to photodisintegration? But I told you we're going to ignore 3 of those, and so I can get this to simplify quite a bit. Remember, we describe the fact that linear attenuation is dependent on the energy of the X-ray beam. So at 30 keV, right, notice that the decay constant here is bigger than it is at 60, right? We are going to take more out of this beam through soft tissue than we are at 60. Higher energy X-rays pass through soft tissue, or any material, frankly, more easily. And notice that, of course, it's dependent on the material. So here's the linear attenuation coefficient for soft tissue at 30, and here it is for bone, right? Bone is going to stop many more of the X-rays per unit thickness than soft tissue is. So just a rough idea what those numbers mean. I mentioned the fact that for us, we're really going to think of linear attenuation really only having to do with photoelectric effect and Compton scatter, right? We're going to simplify that equation for that. And so really this linear attenuation is really just the function of the average Z of the material, right? The Z has to do with how tightly bound those inner shell electrons are, where the K edge is, so the photoelectric effect, and also that electron density. That's going to be the Compton effect that we're going to see. Now before, when I showed you those plots actually were mass attenuation coefficients, not linear attenuation coefficients. And the main reason for that is if you think about water, if you think about the gaseous form, the liquid form, and the solid form, steam, water, and ice, they all have different linear attenuation coefficients. And so the mass attenuation coefficient says, look, just divide by the density of the material, and then all states of water will have the same mass attenuation coefficient. So when people make graphs of them, they tend to make graphs of mass attenuation coefficients, just so that the particular density of that molecular structure doesn't come into play. So here's a mass attenuation coefficient. Before I was showing you cesium iodide and soft tissue. I just wanted to show you these. This is gold. Right? This is iodine. This is calcium. This is calcium. This is gadolinium. This is calcium here, and this is soft tissue. So someone tell me, sorry, what does this discontinuity due to? Right, this is due to the photoelectric effect. Right, this is the K-shell binding energy for gold. And so just above that energy, gold appears more highly attenuating to X-rays just above that energy than it does to X-rays just below that energy, right? That's really kind of odd. Look at here. Look at iodine and gadolinium. Do you notice that iodine is below gadolinium, and then all of a sudden, iodine is more attenuating than gadolinium right after we go over the K edge. And it stays there for a little while, right? So if we're going to image with something like iodine, what we would really love to do is make sure that our KVP that we put on the X-ray tube is such that it generates X-rays that have energy that are just above the K-shell binding energy of iodine, right? That's how we'll utilize iodine as a really good contrast agent. Make sense? Now, what's going on down here in soft tissue and calcium? Why don't we see those discontinuities there? Well, do you notice that this starts at 20 keV? So those exist, right, for those, but those are much lower Z tissues, and so therefore those little discontinuities would be much lower down on the graph. Okay? Good. I wanted to make sure I talked to you about linear attenuation coefficient, but frankly, this decay rate, which is what linear attenuation coefficient is, it's a hard concept to put your mind around sometimes. We're much more familiar with something like the half value layer, right? How much thickness of material does it take to reduce the number of X-rays in 1/2? right? That's a much easier thing for us to understand conceptually. And that's a measure of the quality of the X-ray beam. And I want to introduce that concept, quality, right? It really tells us how energetic the X-ray beam is, right? Because the more energetic an X-ray beam is, the greater the thickness, the greater the half value layer is going to have to be in order to decrease the number of X-rays in that beam by 50%. There's a concept called the 10th value layer that's just the thickness that reduces it to 10%, but usually we work with half value layer. So here we are. I want to start off with kind of a medium energy monochromatic X-ray beam. So a single energy X-ray beam, and it's kind of medium energy. We put 2.5 millimeter aluminum sheet in front of it, and notice now we've reduced its number of X-rays by 1/2. So the half value layer of this X-ray beam is 2.5 millimeters of aluminum. If we wanted to, we could put gold in front of it, and we could figure out what its half value layer was for gold, and that would be a different thickness of gold, a slightly lower thickness, because gold is more highly attenuating, has a higher Z than aluminum. And then if we put another 2.5 millimeters here, it should again reduce the number of X-rays in the beam by 1/2. That's what we mean by the concept of the half value layer. Here's a low energy monochromatic X-ray beam. We put 2.5 millimeters of aluminum in it, and look, only one makes it through. So this is too thick to be the half value layer for this lower energy X-ray beam, right? So we have to go to a thinner piece of aluminum to find the half value layer. So right away, it should say to you, right, okay, this thickness that they're reporting as a half value layer, it tells me something about the energy, the average energy of that X-ray beam, right? And so you'll notice that in most states, there's some sort of legislation that says that if you've got an X-ray machine, that the half value layer from the X-rays produced by that machine has to be at least 2.5 millimeters of aluminum. And what they're saying is the average energy has to be above a certain level, right? Otherwise, you're just imparting a lot of dose in the patient without getting good information for your image, okay? So a lot of times that's expressed that way. The half value layer has to be above a certain level. But you know, we have polychromatic X-ray beams, and things get a little more complex, right? Our X-ray beam that we create from an X-ray tube isn't a single energy, but it's a bunch of energies. And so here's that polychromatic beam. We've got the different energies here. We put 2.5 millimeters of aluminum, and now notice we've got half as many X-rays. Notice a couple of things though. We've got much fewer of the lower energy X-rays and kept quite a bit more of the higher energy X-rays. The average energy of the X-ray beam is now quite a bit higher. So now we put another 2.5 millimeters of aluminum in front of that, and notice that now we don't drop the intensity of this X-ray beam by half. Right? It's not quite dropped in half anymore because of this preponderance of the higher energy X-rays. When you have a polychromatic X-ray beam, the second half value layer is always greater than the first. Because with a polychromatic X-ray beam, we preferentially take out lower energy X-rays. The mean energy of the beam gets higher. The quality of the beam gets higher. The quantity always gets lower with filtration, but the quality, the average energy of the X-rays that you have gets higher. Okay? All right. We already mentioned this fact here that in most states there's this legal minimum. We talked about the fact that monochromatic beams, second half value layer, exactly the same as the first. In polychromatics, second is always greater than the first. Here's the half value layer for some tissues. We've got monochromatic X-rays here, half value layer of soft tissue, bone, and lead. And I just want to make a couple of points, right? Think about it about 60 keV, which is kind of the average energy of the X-ray beam for an abdominal radiograph or so, right? The half value layer is 30 millimeters of tissue, right? I'm just going to assume I'm only made out of soft tissue, right? But from my left side to my right side, you know, maybe 30 centimeters, right? So 300 millimeters, so 10 half value layers. So we start off with our X-ray beam. The first half value layer gets reduced in half. Second, a quarter. Third, an eighth. Fourth, a 16th. fifth, a 32nd, sixth, a 64th, right? 128, 256, right? 512, 1024. When you get to the other side, only 1 in 1,000 X-rays are making it through unaffected. Okay? Remember I told you that most of the X-ray dose, right, 2/3 of it is going to be absorbed by the patient. 1/3 of it is going to be scattered out. You probably said, well, what are we making the image with? Well, we're making the image with that 1 in 1,000 X-ray that strikes the film, plus, unfortunately, the scatters that strike the film as well. Okay? So just keep that in mind in terms of that. So let's talk a little bit about X-ray production here. So the X-ray generator has this power supply on the X-ray tube. It has some timing and exposure circuits. You know, here's some typical values that I've shown you already for an X-ray tube. We've talked about how big a sink of power it is. Here's an old control panel, right? This has been replaced with, you know, computerized units that select these things automatically. But back in the old days, right, you hit your voltage by picking a button here and your current here and your time here. A similar thing is happening now. It's just more under kind of computer control rather than human control. And you can just see how large one of these generators are to power these X-ray units. So we place that large voltage across that X-ray tube between that cathode and that anode. And we put a small voltage across that filament, which is part of the cathode. And we boil those electrons off the filament. And because of that large voltage between the anode and the cathode, they get accelerated towards that cathode and strike it with a tremendous amount of power. So that kinetic energy of those electrons is transformed into heat and X-rays as those electrons strike the anode, right? We've talked about how with that Bremsstrahlung radiation, we produce X-rays when an electron interacts with matter. So here's an old X-ray tube. Very simple, right? You screwed this into a socket here, which gave your voltage across your little filament, as well as your common terminal for connecting your high voltage between here and here, positively charged here. So now when those electrons boiled off the filament, they accelerated towards this, struck it, and X-rays were produced. Modern tube is much more complicated with this rotating anode. I apologize, I've misspoken a couple times when it said cathode when I meant to say anode. Here's that filament when the X-rays are boiling off the surface of it, accelerating to there. Here's our motor, right, rotating as those strike. So here's that Bremsstrahlung we talked about, right? That kinetic energetic electron gets its path changed by the nucleus of that atom, and we give rise to that energetic X-ray photon. Bremsstrahlung produces a continuous spectrum. Sometimes we get Bremsstrahlung X-rays that are down very close to zero energy, and we can get them as high as the kVp applied across the tube. After all, what is 1 electron volt? It's the kinetic energy that electron has when we accelerate it across 1 volt. So if all of its kinetic energy is converted to X-ray energy, then the most that could be would be the kinetic energy that the electron had when it struck it, which is determined by what the voltage was across those two. The closer the electron passes to that nucleus, the higher the resulting X-ray energy. The efficiency of production, if you take the kVp you've applied across the tube and you multiply it by the Z of the anode material that you're using, and multiply by 10 to the minus 6, it'll give you a rough idea of the efficiency of production of X-rays. Remember, we talked about when those electrons interact, producing Bremsstrahlung radiation is only one of the things that they do. They do some excitations and some ionizations and those kind of things, and they produce some Bremsstrahlung radiation. Less than 1% of the energy is used to produce the X-rays. This is basically a big heater that produces an occasional X-ray for us, right? So here's that unfiltered Bremsstrahlung, right? If you applied 90 kVp across the tube, this is what you would get. There it is. Often in books, they just show you this filtered, okay? I want you to realize that's what the spectrum looks like if you could somehow measure it before it got outside of the tube, because even the glass of the X-ray tube is going to filter out some of the really low energy X-rays, right? So that's the unfiltered, here's the filtered. I want to mention characteristic radiation. We've also talked about the fact that these electrons may kick out some inner shell electrons of the tungsten, and then those K shell electrons are going to be replaced by their L shell electrons coming into place. And when that transition from L to K occurs, we're going to get the emission of K to L characteristic radiation. So we're going to get those bands, those peaks. And here it is for K shell. So these are the transitions from L to K, M to K. We also have some low energy ones down at the L shell, right? And here's where an L shell gets kicked out and gets replaced by an M shell or a shell further out. So those are the characteristic X-rays of tungsten. By the way, our electron better have at least kinetic energy 69.525 kVp, right? If we didn't put that across the X-ray tube, then our electrons are going to not have enough energy when they strike the anode to kick out any K-shell electrons, and we won't see those peaks, right? So if we applied 60 kVp across the tube, we wouldn't get the K-shell peaks, only the L-shell peaks. Here's molybdenum, right, that we use sometimes in mammography imaging. Here's the K-shell characteristic X-rays for molybdenum. So we got to combine those together, right, because the characteristic and the Bremsstrahlung are happening together. So here's that unfiltered spectrum, the L-shell characteristics with the K-shell characteristics. But most books, again, show you this picture, right, where it's already been filtered a little bit. All right. So beam quantity, I've already mentioned that once. It's the intensity. It refers to the number of X-rays in the beam, just the number of X-rays. Beam intensity can be affected by beam filtration. If we put a filter in front of the beam, we're going to decrease the intensity of the beam. If you put anything in front of the beam, the patient in front of the beam, the intensity of the X-ray beam on the other side of the patient is decreased. The further we get from the X-ray source, the less the quantity is going to be. We talked about the R-squared effects. Time, the less amount of time you're in front of the beam, the quantity is going to be decreased. And the current. If you change the current that you apply to the X-ray tube, which is the number of electrons that are being boiled off the filament, right? So if we increase the small voltage across the filament so that more electrons, it heats up more and more electrons get boiled off of it, keeping the voltage across, the really high voltage across it the same, now more electrons are flying across. When they hit the anode, they're hitting them with the same kinetic energy, but there's just more of them. We've increased the quantity of the beam. Doubling that current doubles the number of X-rays produced. Doubling the amount of time that we image for doubles the number of X-rays that were used. And so we usually say that that product, the current times the time, the milliamp seconds, is the important quantity. Certainly, if you want to image something that's moving, you'd like to get that time small and maybe bump that current up, right? Because they're not quite equivalent in living humans who may be moving, right? Time may induce some blur. So here's that beam quantity. Tube is doubled, right? And notice the output at every energy is doubled as well. The quality of the beam refers to the average energy of the beam, right? We've got this polychromatic beam and its average energy. And it's not just the kV across the tube that determines that. It's what the target material is, tungsten. And then the amount of filtration that we use before that. So what determines this is a little bit complex. But in average, in most of our radiographic imaging, it's about 1/3 to 1/2 the kVp that we put across the tube. If you'll divide that number by 1/3 or 1/2, it'll give you an idea of what the average keV, the average energy of your X-ray beam is. Okay? We talked about increasing the voltage increases beam quality, but if you increase voltage, you also increase the quantity of X-rays that were produced. Do you remember our efficiency equation? Our kV times our Z times 10 to the minus 6. If you increase kV, you make more X-rays of every particular energy, okay? So here's that picture. Notice if we increase to 75 to 90, yes, we can make some more highly energetic X-rays, but we also increase the number of X-rays at every single energy. So increasing kV both increases the quantity and the quality of the X-ray beam, okay? Here's our tube filament. Notice in a lot of tubes you've got two. The bigger this is, the larger the focal spot is, and so the poorer the resolution properties of our imaging system. Here's a nice modern tube where we've got this cathode. We're boiling electrons off. It has this focusing cup, this positively charged focusing cup, because after those electrons are produced, they're all negatively charged. They want to spread away from each other as they travel over towards the anode. So we kind of force them towards each other with that focusing cup. Here's that focal spot. We've got our X-ray beam coming in, right, from the cathode. It strikes the X-ray beam, and the bigger this filament is, the broader this electron beam is. And so the larger area it ends up striking on the anode. And the larger area it strikes on the anode, you know, our sharpest image would be if all those X-rays look like they came from a single point source, right? And so the broader the area that it looks they come from, the poorer our resolution properties of our imaging system. But I want you to notice something else, right? Notice that when this comes in, X-rays are produced via Bremsstrahlung. The ones that head this direction have to pass through more tungsten than the ones that head this direction. So the X-rays here are lower in intensity, the number of X-rays here, than they are here. This talks about some of the techniques that we use, kind of different values that we use for some of those. We deposit an awful lot of energy in that X-ray tube, right? We deposit a tremendous amount of energy here, which is why we rotate an anode. We make it out of something like tungsten. We try to coat it in some oil to help dissipate that heat and prevent it from being destroyed. Filters preferentially absorb those low X-ray energies, thus removing X-ray photons that would add to patient dose without adding to image quality. So filtration reduces X-ray output at all energies. It reduces the quantity of the X-ray beam, but it increases the average energy. It increases the quality. So here we go, right? Filter. Decrease number of X-rays, decrease quantity, but higher average energy, higher quality of the X-ray beam. That's that filtration. The average energy is higher, but the number of X-rays is smaller than the unfiltered. Beam hardening refers to the preferential loss of those lower energy photons from a polychromatic X-ray beam. What does that mean? Filtration hardens the X-ray beam, right? Filtration hardens the X-ray beam. It makes the average energy higher. So if we want hard beams, beams that are going to penetrate things very nicely, like if we're imaging through this pelvis with the bones there, we want a higher kV with some heavier filtration. Beam hardening, I just showed you, right? It's the same picture as for filtration, because that's what filtration does, harden the beam. The Heal effect I want to mention one more time. Remember we mentioned that the intensity of the beam is lower here, higher towards this side. With respect to the central ray, quite a bit of drop off. How can we eliminate that or minimize that effect so that our image isn't brighter towards one side and denser towards the other side? Well, we've got a couple things. You can change your anode angle so that the variation across the X-ray beam is smaller. There's less variation across it by making this anode angle bigger. You could move further away from the X-ray beam. Instead of here where the variation is 75% to 120, if we'll move to this distance away, we're 90 to 105. Remember, the intensity of the beam is decreased, so we might have to image for longer or increase the MA on the tube there, right? But this is what we do for chest imaging. We image from 6 feet away so that we get less of that kind of effect. Or in mammography, where we take advantage of the Heal effect and we put the cathode side of the tube where the intensity of the beam is higher towards the thicker part of the soft tissues, okay?